Hi guys, let's take a stab at this question, minimum window substring. So basically we are given two strings S and T, and S is the a larger string, so think about it like the master string, and T is the substring. So we have to find basically T in S. So so all the characters in T should be available in S substring. So for example, here A, B, C should be present in here. So for example, if we take this substring, so we see A, B, and C, and the length of this is 6. So the question is we have to minimize this window. We have to find the minimum window in S where all the characters in T are contained, and we have to return that minimum length, minimum window substring of S. So how do we go about this? The first thing is we have to count the number of characters in T. So the obvious thing to do here is do a hash map. So we'll construct a hash map here, and then we'll have a window here. So this will remain constant in time. So here we'll say A1 because there's one character of A, one B character, and one C character. So we'll have our hash map, and then we'll do a running window, a sliding window of sorts, and we'll do a count of all the characters in in the window. And here we'll continue to build the window. For example, we'll have here 1A, 1D, 1O, 1B, 1E, and then we add a C. As soon as we add a C, we'll be able to see. So we can have another function. Basically, that function, what it will do is it will check whether all the characters contained in this hash map are in fact present in this window. And the complexity of that function would be constant because it would only have to traverse through all the keys in this hash map. So only we have uppercase alphabets, so at most we could have 26 characters. So this function is guaranteed to run in O of 26, so that's a constant. But other than that, what we'll do is this returns false. It's not going to match up. As soon as we hit this thing, this will be a true. So we'll capture the length, which would be 6, and we do not have to return the length, but rather we have to return the output itself. Or what's that substring? So here it's a length of 6, and this would be the substring. So once we stumble upon the correct answer, what's the next order of business? Well, in that case, we'll have to move our left pointer because we already got this string here. So we knew the last character was important. Without it, we had to continue moving forward because the string did not match. But that does not mean the first character was important. In this case, it was, but it could have very well been the case that this AD could have been a DA. So let's start shedding from the left. We start shedding from the left. We remove A, so we are left with the string DOBEC. Well, in that case, it's no longer a match because we do have an A here, but we do not have an A here. So what we'll have to do is we'll have to start incrementing our right pointer again. So we'll add O, D, E, B. None of these do any justice because we do need an A. As soon as we get an A, this is the substring we have, and however many characters there are, it seems there are 10 characters here. So we have a 10 character substring, and that does have an A. It has two B's, not one B. Or yeah, it has two B's and one C. Now, bear in mind all these other characters that are not available in T. For example, O, E. These are of no consequence. But anyways, these are so we are not going to be checking them and wasting compute time on this. We'll only be checking whether the characters in T, of however many characters there are actually this in here as well, so that we can do by comparing the hash maps. But once we get this answer again, what do we have to do? We have to start shedding from the left because we already got this string of 10. So we'll have to check whether if we shed this, would this still be a match? So now it would be a match because D was not in the string T to begin with. So let's see, let's shed one more, and then we go on, and we can shed this B as well because this we had two B's. So if we shed this B, then we still have a B. So this works. This also works. If we drop E, this would also work fine. So here we are left with a length of 6, and it still is a match. But once we drop the C, what would happen? Well, now we have an A and a B, but we do not have a C. So again, we'll have to increment the right pointer. and you do that, and now it's again length 6, and it does not match, so we'll have to increment the right pointer again. So now it's of length 7, and again it's a match because we've got a B, we have got an A, and we've got a C. So what do we do next? We start incrementing the left pointer. So D, E, B, A, and C is still good, so we'll continue moving on. And by the way, while we are moving on, we do keep decrementing the size because we have to find the minimum window. So here the size is 6, which we already had in the past. So this is not the least, but it is a match. And this is the string we have, D, E, B, A, and C. So we'll continue moving forward. Now we've got a length of 5. So now this is the global minimum. So we've got a length 5, and it's E, B, A, and C, but we'll keep trying our luck. We'll keep moving the left pointer forward, and here we've got B, A, and C. Again, this is a valid substring because it's got these 3 characters that match. So we reduce the length further to 4, and this is the corresponding output for now, B, A, and C. Now we move it once more and we see A and C. Well, this is no longer a match because we do not have a B. So what we had in the prior iteration is actually the answer, B, A, and C of length 4. So again, the complexity is 26n. 26 is coming from the fact that we will be checking the hash maps. We'll be checking whether all the characters, all the frequency of characters available in this string is at least present in this window for it to be a match. So let's code it up. Now, this question does require to return an empty string if in fact the substring is empty. So let's do that. So if t is empty, then return an empty string. Okay. And let's define our hash map. So we'll do, so window would be the hash map for this, and this would be changing per each iteration, and t count t is basically the hash map of this. This is going to be a constant. So let's just fill in count t first for c in count of t. So for c in count of in t. So for this, and then we'll say count t of c is equal to 1 plus count t dot get c comma 0. So essentially we are filling in this count t hash map, and the reason we are doing dot get is because we do not want a key error if the character is not present in the hash map to begin with. If it's not present, it will give 0 in the first iteration, so 0 plus 1 becomes 1, and then going forward it will be fine. So this would look something like, for this particular first example that we were looking at, this is how this will look, right? Cool. All right, so now we also need two variables, result length, which should be minimized, and result itself, which should be the output string. So what can we can give result length as length of s, because we have to minimize it. So we can start with the maximum value, and the maximum value can no longer be, cannot be greater than this length of string s itself. And result, initially let's give it an empty string, because ultimately this will have to be a string. So left pointer will be 0, here will start here, and then for r in range length of s, so we have to keep incrementing the r pointer. Now what is the first order of business? We will have to add this character to window dot get s of r comma 0. So we add the first character to the window hash map. Now we need to check whether at this point, once we added this character, is this does this hash map have all the characters from hash map in t, and is the frequency greater than or equal to that of t? So why don't we just break from here and just define another function? So let's define this function is included, and we always have to give reference to the objects of self. Let's call s1 and s2. So s1 would be, in this case, we'll be passing it for the window, meaning this is the master one, and s2 is the sub hash map for t, so we'll have to check whether all the values in S2 are available in S1 with the frequency greater than or equal to that in S2, right? So, and what would be the return type of this? It should be a Boolean, and we'll say return. So basically we'll say for every key in S2, if S1, now we cannot say S1 dot key directly because it might not even, it might be possible that we have not seen that key yet in S1, so that will give a key error. So we'll, let's say dot get for this key, and if it's not available, we'll give it a 0. If this is less than S2, and here we can give the key because we are actually referring these keys from S2. If this is less than what was available, and so anything that's greater than or equal to is fine, but if it is less than, what will we do? We'll return a false. But if it traverses through all the keys in S2 and does not return a false, then we'll return a true. So yeah, so this should be fine. So now using this function, we can check whether our window is valid or not at this moment. And what would we do? Why do we want to check that? So if it is not valid, then it should basically ignore this function. But if it is valid, then we have to decrement from the left side. So we'll say while, because it might be that we have to decrement multiple times. So we'll say while self, and self is the reference to this function because it's on the same level as this one. So while self dot is, I'll say is included, and then we'll pass window as S1 and count of t as S2. All right, that looks fine. And we'll say if r minus L plus 1. So this is the length. Uh, this is the length of the current window because we do want to minimize the length. So we have to check this. If this is less than, so first, whether this is even, so in the first iteration, this is not going to be valid. So this is not going to run this function, but we have to run this function when it is valid. So which is what we are checking here. But on top of that, we also have to check whether this is uh, less than the global minimum that we had so far, in which case we'll have to update this. So we'll say res length is equal to what? Is equal to minimum of res length and r minus L plus 1, right? Well, we could just say res length is equal to r minus L plus 1, but this is fine because there's an equal to sign here. And what is result? Result would be S of L, and this will go on until r plus 1. Why would it go until r plus 1? Because this is non-inclusive. So we are including, basically the result would be from index L to index R being included and r plus 1 not being included. So first we compute, because this is valid, we compute the corresponding result, but we do not stop here, because now what is the next thing that we have to do? We have to remove the leftmost thing to see whether there's a smaller window. So let's do that. S of L minus equals to 1, and L will, we have to increment the L pointer. So here when we went down here, it was a match. It was a match until here, but we do not stop here. We'll have to shed this and we'll have to keep checking. So yeah, this was valid. So this would have updated. It would have said, oh, this is this valid? And it would have said, yes, this is valid. So we would have computed the minimum length, but then we would not have stopped there. We would have shed the left most, incremented this left pointer, and then we would have checked this thing, and so on and so forth. The thing is, we have to check it first whether it is valid, and we have to compute the result before we start decrementing it. So the last one that is captured, uh, we cannot do it afterwards, because if we do it afterwards, we would have lost the value. So I think this does it. And now what do we have to return? We have to return the result itself, not the resultant length. So see, it does give BANC as the output, and let's submit. All right, so it passes fine, and as we spoke about, the complexity of this is O of 26 times n, which is kind of equivalent to O of n. All right, see you guys.